what I want you to be able to do today is I want you to be able to follow what I'm doing. You might not be able to come up with any of it on your own yet, but I want you to be able to follow what I'm doing. And then, hopefully from that, as we do more and more examples, it goes from, oh, I can see what Mrs. Hyatt's doing, and like, oh yeah, I remember Miss Hyatt did that, I can do that on this problem as well. And you will start to like come up with the answers on your own. Okay, so we are going to have a quiz next week. I'm not sure, probably Tuesday. Probably Tuesday. Is Tuesday bad? Oh, Tuesday's your birthday, isn't it? It's okay. This is not a bad quiz. This is not a birthday ruining quiz. Because this is just the formula quiz. So just like unit circle, even though I would argue this is much easier than the unit circle because there's not as much on it, we will have a quiz that will just be basically these first, well, not the first four, slides 2 through 5 here. Reciprocal identities, we have already went over these, I'm pretty sure at some point. Sine is 1 over cosine, cosecant is 1 over sine, cosine is 1 over secant, secant is 1 over cosine, tangent is 1 over cotangent, cotangent is 1 over tangent. These will be on the formula quiz. You have to have them memorized to be successful with verifying trig identities. So they're called reciprocal because that just means when you do 1 over something, it just flips it. There's also the quotient identities. Tangent can either be sine, it can be sine over cosine, and cotangent can be cosine over sine. We use that when we were doing unit circle stuff. So that one should be one you've already seen. It shouldn't be terribly difficult. What I do see sometimes is tangent over here is 1 over cotangent and 1 over tangent. Right? For reciprocals, all of these should be 1 over. The quotient identities are the ones with sine and cosine. What I see sometimes is students get those mixed up there. So make sure you've got those. All right, Pythagorean identities. This one should be new. I do not believe you guys have seen these at all. So we got sine squared theta plus cosine squared theta equals 1. There are a couple notes that we need to make about this. First of all, some notation, because I don't think, other than possibly a little tiny bit you may have seen in Math 3, that you have seen this notation, sine squared theta. It looks like you're squaring the sine, but you can't really square the sine because that is an operation, right? Mathematicians, in order to, in order to simplify so that they didn't have so many parentheses everywhere, they decided that if they had something like sine of theta squared, they were going to write it this way. They were going to put that little square right there to mean sine of theta squared. So when you see sine squared theta, it means the whole thing, sine of theta, is squared. I believe that they probably did that so that they would avoid like a lot of parentheses, because sometimes if you have like a complicated expression here, you may end up with a lot of parentheses, and then you got those extra ones on the end. So, so this is an important note. Sine squared plus cosine squared equals 1 is one that we are going to use very often. I could go through and show you where it comes from, and I might one day, but I don't think we will right now. Most students remember this one. Like if you go ask my calculus class, I doubt they remember either one of these bottom two, but they probably remember sine squared plus cosine squared equals 1. This one we will use a lot. We don't use these bottom two as often, although they do show up. Let me show you how you don't even really have to memorize the bottom one. I had a student ask me one time why this one has the plus 1 at the end and this one has the plus 1 at the beginning. Because really, does it matter which place you put that? It doesn't, because addition is commutative. And I got to thinking about it, and it made me realize, I probably should have realized this long before, but that seems to happen to me sometimes, that this is why the 1 is here on the second one, and the 1 is here on the first one. If I take sine squared theta plus cosine squared theta plus 1, which is the one you're going to use so much, you're probably going to remember it pretty easily. if I divide everything by cosine squared theta, that is a legal move because I'm doing it to everything on both sides, right? If I divide everything by cosine squared theta, sine squared theta over cosine squared theta is tangent squared theta. This would be 1. This would be secant. Okay? So, if you just remember that, you don't really have to memorize the second one. The third one, you don't really have to memorize either, because if I start with that same thing again, this time if I divide everything by sine squared theta, this gives me 1, this gives me cotangent, this gives me cosecant. So, I am not a great memorizer of things. I go to a lot of lengths sometimes to not memorize things and just use like logical conclusions for them. You may be an excellent memorizer and you may just be like, I don't even understand what happened there. I would rather just memorize these. That is fine. But I love finding ways around having something memorized. So this helps me remember. And honestly, like I really do this in my head whenever I'm trying to remember those second two on this one. All right, so Pythagorean identities, those are new. You are going to need to have those memorized for the quiz. And then the last one, we are not going to use very often, but we are going, they will be on the quiz, and you can use them. Let me say that. Okay, they're not going to be ones that we use a lot, but you can use them. You also can get by without knowing these, except for they will be on the quiz. So, sine of negative a equals negative sine a. That a could be a theta or x. It doesn't matter what variable you use. I don't know why I used a. Probably our old textbook probably used that. So, what this means, and then cosine of negative a just equals cosine of a. If you think about what the unit circle looks like, over here, both things are positive. Over here, we got negative, positive. Over here, we've got negative, negative. And over here, we've got positive, negative. All right. So, our first coordinate is cosine, and our second coordinate is sine. When we make our variable negative, that flips over to the opposite side. So if you look at what's happening here with these, cosine, whenever you flip this over, it does not change signs, but sine does. So whenever we have sine of negative pi over 6, so pi over 6 would be here, sine of negative pi over 6 is here, we get the same absolute value, we get square root of 3 over 2, but we're going to get the opposite sign. Whereas with cosine, if we did the same thing, pi over 6, we would get the exact same value. So this is just something you can use with your unit circle. You don't have to. You can just think about the unit circle like we've been doing. Sine of negative pi over 6 would be negative sine of pi over 6. And then sine of pi over 6, which is right here, is, well, I said square root of 3 over 2. It's 1/2 there. So sine of negative pi over 6 would be negative 1/2. You also can just think about going backwards on the unit circle. You don't necessarily have to use this trick. Cosine of negative 3 pi over 4 is going to be cosine of 3 pi over 4. And cosine of 3 pi over 4 would be right over here in the fourth quadrant. And that's going to be negative square root of 2 over 2 for that. Opposite angle identities will be on the quiz. You can use them or not, just do unit circle like you've always done. It's not a big deal. Either way, make sure you don't forget the opposite angle identities on the quiz, though, because that's the most commonly forgotten one whenever kids are studying, because it is the one that we'll probably use the least as far as actually working out problems. Okay, questions? All right, so we've got all of our identities. We must have those memorized right now. You may not have memorized, especially that Pythagorean identity, so you may have to refer back to your sheet, but by Tuesday next week, we got to have them memorized. I will give you guys a quiz. In fact, let me just show you what that quiz is going to look like. I'll let you see the exact quiz that you will be taking. It will look just like this. Reciprocal identities, you got 6 blanks. You're going to list what was on that second slide there. Question identities, you got 2 blanks. List what's on that third slide. Fourth slide is Pythagorean. The last one we just did is opposite angle. That's all it is. So Tuesday we will take that. Counts as a full test, not test, full quiz grade. So don't mess that up. This should be easy points for you. So make sure you're ready for that. All right, let's talk about verifying trig identities. Okay, so this is the closest thing you're probably going to get to in high school anyway, of doing this, and in Math 2, you do a little bit in Math 2, of doing mathematical proofs. These are not exactly mathematical proofs because I'm not making you justify every step that you make. In Math 2, although you guys probably had some crazy Math 2. You guys may have been. Some of you did and some of you didn't. It depends on what semester you ended up having it. Some of you were probably at your house given assignments to take pictures of trees or something. Others of you may have actually had Math 2, depending on what semester you had it. But Math 2, you do 2-column proofs on triangle congruence. So it's that angle, side, angle. Anyway, if you major in math, if you decide this is what you want to do, because I did not realize it was going to happen whenever I went to college, mathematical proof is a big thing, justifying why something is true. I thought you just did harder and harder and harder math problems until you mastered every math problem in the world, which was true for a little while till I got past like Calc 3 and linear algebra. And then everything turned into proof classes. So I had classes like advanced calculus, which I thought was really hard calculus problems. No, it was the proving of calculus. It was writing these like page-long proofs of why things you learned in calculus were true. And then I had modern college geometry, which was exploring other geometries, like spherical geometry. Yeah, it is crazy. And then writing proofs about why spherical geometry theorems were true. In spherical geometry, a line is a circle, in case you want to know about it. Yeah, it's basically what you would need, like if you're looking at the globe, which is roughly spherical, you have to, your geometry completely changes. Like, every geometry you've learned is Euclidean geometry, which is like, well, it can be 2D or 3D, but it can be graphed in the coordinate plane. We're talking about X, Y, and possibly even Z, although you don't do much with Z in high school. Z would make it 3D if you had 3 axes. But you're talking about distance, you're talking about, like, everything we do is Euclidean geometry. But spherical geometry is like our plane is now our sphere. So if you think about like a line, would be like if you got in a plane and you flew straight and you never turned, right? So what would happen if you did that? Like whatever direction you went in, assuming you don't crash and you've got plenty of fuel, you just, fly, leave Elkin, take off at the airport, and fly straight forever. What's going to happen? You're going to go in a big circle, right? You should end up back over top of Elkin, and then just keep on going, right? That is a line in spherical geometry. So a line is a circle in spherical geometry. Anyway, that's totally unrelated to what we're talking about. But this is going to deal with proving why something must be true. So the cool thing about this is that they give you the answer to every problem. Every problem, unless there is a mistake in the problem, and I really haven't varied from the problems I've used in this a lot for the last while. Sometimes I'll pick different numbers that you do, but I have not seen many in a while that have errors in them. Unless there's an error in the problem, you're starting with a true statement. So it is true that sine cubed x plus sine x cosine squared x equals sine x. What you have to do is prove why that's the case. Okay? So, for this, you may not move anything from one side to the other. This is not like an equation that you're solving. You are trying to prove that this statement right here is true. So what I do whenever I start all of these is I draw a line down my equal sign. And you can only work on one side or the other. Nothing can go from one side to the other. So like, I cannot subtract sine cubed x. I cannot subtract it from both sides. I cannot move anything from one side to the other for these. What I have to do is do work on one side or the other, or possibly both, to eventually get down to where both sides equal the same thing. Okay, so let's look at this problem. I've got sine cubed x plus sine x cosine squared x. I need to do something that is going to prove that this has to equal sine x. So, there's a lot of different things that you can do. It may be helpful for you to sometimes think of sine and cosine as just like variables. If I had x cubed plus xy squared, right? Sine here is my x, cosine is my y, if I'm thinking of it like that. Is there a greatest common factor that I could pull out of that? What could I pull out of both of those terms? I could pull out an x, right? So I could write this as x times x squared plus y squared, right? So in just variables, I could do that. I can do something similar with sine and cosine. I can treat them like they're just a variable. So I can factor out sine of x, and then if I pull out a sine x, here that would leave sine squared x, plus here the sine x is going to be gone. I'll just have the cosine squared x. Okay, now if you were in college math and you were doing this, you would have to write a statement showing that you did that, and then use whatever property you used to prove that that was true. So I don't know if I can remember what property that would be. It's the greatest common factor, but I don't know if I know what the property would be for that. I probably once did, maybe. I know what the next one would be. But you are not going to have to worry about that. I'm not going to make you write out a long proof. I should show you guys my math notebooks sometimes from college. I didn't realize that's what I was getting into whenever I majored in math. If you do math education, you might not have to do all that. But at Meredith, there was no math education. You had to get a straight math degree. So I have a straight math degree that goes a little beyond what you need for teaching sometimes. So does this look familiar? Sine squared x plus cosine squared x. We just saw it a minute ago. What was it? It was, I don't know if I want to do that. It was Pythagorean identity, and what was it equal to? 1. So, sine squared x plus cosine squared x equals 1. Those identities that I have given you, those are true statements. They have been proven by mathematicians that they are true. I could go through and show you a proof for some of them. I'm not going to because of the length of time that it would take. But sine squared plus cosine squared equals 1. So since they're equal to each other, I can substitute. So now one thing that's important about this is you have to show all your steps. You've got to show where you substitute. So you're replacing sine squared x plus cosine squared x with 1. So we're going to show that. And then what is sine x times 1? Sine x. And that equals what is on the other side. So you are done with this verification. So you've always got the answer. If you get down to the bottom and you've got the same thing on both sides and have not made any mathematical errors on either side, you know that you have done it right. If you don't get to what's on the other side, then you know you're not done. It's not correct yet. Now, let me emphasize a few things about this. For these problems, showing your work is going to be important because you should already know the answer, right? Sine x should equal sine x here. So if you don't show any work and you just go straight to the answer, then you have not shown me that you know why that is the case. You have just shown me that you listened for 2 seconds while I told you that the answer is always the same on both sides. So make sure you're showing your work. Let me also say on the other side, you know that you need the same thing on both sides always, right? So hopefully those are screams of joy and not pain. I can't really tell. But I think there sounds like there's laughing in there as well. Yeah, we're going to save ourselves and hiding here for the.
Yeah, that's what I'm saying.
Yeah. We're going to just stay over here. All right. We do have catapults. They're not. That one right there was not near as good as it looked like it was going to be, though.
Is that metal one good?
No, not near as good. Both the metal one and that one had like bungee cords on them that broke, so that messed it up. This year was not. It looked like they were going to be really good, but they were not nearly as good as they looked like they were going to be.
Why don't we get some catapults?
You didn't have me for math and mine. I'm sorry.
You didn't hear we could just build something.
Yeah. Sorry. Okay, so back to what I was saying before we had to get off topic to express our concern for those next door. I've told you the answer needs to be the same on both sides. So if you don't know what you're doing and you're pretty sure you've done it wrong, still put the same thing on the last line of both sides. Okay? There's a chance maybe you were closer than you thought, and I'm going to make an assumption that you knew that last step because you have the same thing. I might look at it and be like, oh, they had no clue what they were doing. They just wrote that down. It doesn't matter. You were going to miss it either way, right? So you always, whenever we take a quiz on this, like the actual quiz where we actually do problems, you always want to make sure you got the same thing on both sides at the end. Even if you're just like stuck, don't know what's going on, and just write it down. It might not help you, but it couldn't hurt you to do that. So here is a list of strategies. It is not a conclusive list of strategies that you're going to use, but it includes several of the strategies that you're going to use. In general, I try to work on the more complicated side first because there's probably more things that can cancel or simplify there. Substituting basic trig identities to simplify, this is things like tangent, sine over cosine. Secant, in general, a lot of times you want to get rid of tangent and secant and cosecant, especially secant and cosecant. They just give you problems. So you can change them to sine and cosine. That's also kind of like what we've got down here. Or if you see something like Pythagorean identity, replace it with 1. Sometimes it may be helpful to do what we just did on the last problem and factor something out, whether it's factoring out a greatest common factor or factoring into 2 sets of parentheses. But then sometimes that's not helpful, and you might actually need to multiply the stuff back together. It just depends on what type of problem that you are dealing with. So these are, again, there's other things that you can try, but this is a list of some things that can be helpful. So let's do another example. All right, we got cotangent of theta equals cosecant theta over secant theta. We have to get the two sides of this to match. All right, so we got to get the two sides of these to match. The right side's a little bit more complicated because it is a fraction, so I think I'm going to start there. And in general, secants and cosecants are just going to give you problems. This is not a Pythagorean identity because you don't have any squares. I would probably go with making cosecant 1 over sine theta, and then making secant 1 over cosine theta. Oh, also, another thing for this, please always work down, okay? Because if you work sideways, it makes it very difficult for me to follow your reasoning. Okay, so please always work down for this. And I'm going to draw these blue lines in between to delineate like step 1, step 2, step 3. You may want to do that because especially with like the complex fractions, sometimes they kind of run together and it's hard to tell what you were doing. So, dividing fractions, what do we know about it? Easy as pie. Flip the second and multiply, so I could write this as 1 over sine theta times cosine theta over 1. If I multiply those together, I just multiply straight across for fractions. So it's going to be cosine theta divided by sine theta. And what does that equal? It is not tangent, but cotangent of theta which is what we have on the other side. Okay, let me give you another option on this as well. It would be okay if you did like this. Maybe you don't put that last step right there. And instead, you say that cotangent is cosine theta over sine theta, which is true, right? So maybe you work a little bit on this side. As long as you have not made any mathematical errors and what you have at the end is the same on both sides, then you would know that that's correct. So you could do it the way I just had it, or you could work some on both sides and it would be okay. Okay, questions? Yes? You don't necessarily. In general, I will tell you that there are not many times on these problems that cotangent is going to be 1 over tangent. You can do it that way. Like I could do 1 over tangent theta, which could then be 1 over sine theta over cosine theta, which could then be 1 times cosine theta over sine theta, which would be this, but it's a lot easier just to use the quotient identity from the beginning. So 1 over tangent is not used a lot. It could be used, but it's not used a lot. So that's a good question, which is one of those answers, like you just kind of have to try it and see if it works, and it may not. It also is possible, like, Liam, you may have seen this and done it this way, and Abby may see it and do it a different way, but you could both be right. Also, especially when we get to the more complicated ones, there are several ways you could do them. So, so it's all about making sure you don't like break mathematical rules, more so than like having to do it a certain way. I always love it whenever like students come up with really like strange ways to do a problem that I haven't thought of that are actually still right. So I always find that interesting how some people's brains work differently than others. All right, so for 3, secant squared theta minus tangent theta cotangent theta is a little more complicated on that left-hand side. And for this one, I'm going to go with what I know the most efficient way to be. One reason that it is very hard for me to teach this is because I have done a lot of these in my day. And I'm not saying that whenever I was in high school I was necessarily like able to do them super, super fast, but I usually can see how to do them. So sometimes it's hard for me to explain how that happens. But in general, secants and tangents and whatnot make it more difficult. I could on this problem change everything to sine and cosine, but I've got a secant squared, and then I've got a tangent squared over here, and that kind of seems like that Pythagorean identity that was, what was it? Was it 1 plus tangent squared theta equals secant squared theta? Like I feel like I might could go somewhere with that, possibly. So I am not going to mess with this secant squared right now. But tangent, cotangent, that's a problem. But if we think about those quotient identities, they're just the reciprocals of each other, right? So you could actually do this a couple ways. I'm going to do secant squared theta minus sine theta over cosine theta times cosine theta over sine theta. And this is actually a place where if you did cotangent is 1 over tangent, it would work the same way. What's going to happen here is this sine can cancel with this sine, and this cosine can cancel with this cosine. And what happens when everything cancels out like that? What do you have? 1. So now I have secant squared theta minus 1. Now, secant squared theta, right here, is equal to 1 plus tangent squared theta. And I've got a tangent on the other side, so I want to have tangent instead of secant, right? So I could do that secant squared theta, I could replace it with 1 plus tangent squared theta. And then what happens when I subtract this? I got 1 plus tangent squared theta minus 1. The positive 1 right here is going to cancel with the negative 1 right here, and I've just got tangent squared theta, which is what I have on the other side. That is definitely not the only way to do that problem. There's lots of other ways that you could do this problem. But rather than do this problem over and over again, we're going to keep going because we'll see lots of problems for these, so you'll see some more strategies come about. All right, here's this one. Ooh, my. This one looks terrible, doesn't it? I would argue, though, that this one's actually maybe even easier than the one before it. I am going to do this problem the 2 easiest ways that I know to do it. I'm going to do it 2 different ways. I'm going to do it once, then we'll erase it and go back and do it again. So you can see the 2 options here. I said a strategy could be to work on the most complicated side first. So you could make an argument for either side being the most complicated. This one has sines and cosines, which are sort of more simple units when you're dealing with trig. this is secant and cosecant, which can be changed to sines and cosines. So I'm inclined to work on the right side first because I know I can change that to 1 over cosine and 1 over sine. So I think I'll do it that way first, even though this side looks crazier, right? So if I change this to 1 over cosine x, and I change cosecant to 1 over sine x, then these are just fractions. I could put my whole numbers over 1. This will give me 7 over cosine x plus 5 over sine x. And as you're working, you want to be looking over at your other side. Like, oh, I got a 7 here, a 5 here. So that's good, but and I've got sines and cosines now, but this is 2 separate fractions, whereas these are put together, right? So what we want to do here is get common denominators. So this we did a lot with when we were solving rational equations. I've got cosine for this denominator, sine for the other, so the common denominator needs to be sine times cosine. So for the first fraction, I would need to, I'm going to use a different color here, I would need to multiply the top and the bottom of this by sine x. And then for the second fraction, I would need to multiply the top and the bottom by cosine x. That is a legal move because when you multiply the top and bottom of a fraction by the same thing, it's just like you're multiplying by 1. Oh, what do I do with fractions when I add them? Keep the denominator the same and just add the top, right? So when I put this together now, since they have common denominators, I will have 7 sine x plus 5 cosine x over, you don't add those denominators together, it's just going to be sine x cosine x, which, if you look over at the other side, is what we've got. So, not as many steps as it seemed like maybe it would be from the beginning. Alright, let me go back. I'm going to go back and do this one again in a different way. You can write it down if you want, or just over to the side, or you can just watch. So, let me erase this, and I'm going to show you what it would look like if you worked on the left side instead. So, because I also like this way as well. There is a not so mathematical principle that I believe I've used with you before called the love connection. Have I told you about the love connection? The love connection is like if we have 2x plus 3x squared over x, we could divide this by x, and we could divide this by x, and whenever you circle it, it makes this cute little heart, right? Don't do the love connection upside down. It's not allowed. No upside down love connections. But right here, I can do the love connection for this. What you're doing is you're just dividing both of those by that same denominator. So that would look like this. 7 sine x over sine x cosine x plus 5 cosine x over sine x cosine x. And what can happen here? Once we've got these split up, I've got a sine in top and bottom here, and a cosine in top and bottom here. And that is going to give me 7 over cosine x plus 5 over sine x. So I can either go over to this side and change secant and cosecant to 1 over sine and 1 over cosine and 1 over sine, like I did at the beginning of the other problem. Or it is okay, if you have a cosine in the bottom, you can move it up to the top and make it secant x. And if you have a sine in the bottom of a fraction, you can move it up to the top and make it cosecant x, which matches what we have on the other side. Okay, questions? All right, I think we got, let's see, is this the last one or we got? Yeah, this is the last one. Let's do this one. We'll be done. Oh, that's not sure something. All right, so for number 5, I've got sine A over cosecant A plus cosine A over secant A. And I need to verify you're going to pretty much have to do the work on the left-hand side for this one. What I would begin with is I do not like the cosecants and secants. I don't like having them, unless they're squared where they might be Pythagorean identity. I just like to get rid of those. So that's what I'm going to do. I'm going to do sine of A over 1 divided by sine of A. And then I'm going to do the same thing over here for the secant. Cosine of A over 1 divided by cosine of A. And so dividing fractions is easy as pie. You can flip the second and multiply. So this would become sine A times sine A over 1, and here we'd have cosine A times cosine A over 1. What is sine A times sine A? It's sine squared A. So this is sine squared A plus cosine squared A, and what does that equal? That is Pythagorean identity. That equals 1. That is our answer for that. Okay, so hopefully at this point you guys can follow